Welcome all. So, today we will continue our discussion on application of derivatives. In particular, today we will learn about finding the maximum and minimum values of function on a given interval if they exist, and then we will learn about finding the tangent line equation of tangent line and normal lines. So, let me first start with so, we will discuss about finding the maximum and minimum values of a given function f of x on a given interval say I. So, first of all, recall that I stated this theorem before, that if f of x is a continuous function, on a closed interval, we say a b, then the function attains its maximum value and minimum value on the interval a b, which means that is there exists points x naught and y naught in the interval a b such that f of x naught is less than equal to f of x is less than equal to f of y naught for all x belonging to this interval a b. In this case, f of x naught is the minimum value of f of x on the interval a b, and it is attained at the point x naught, which is in the closed interval a b. Similarly, f of y naught is the maximum value of f of x on the interval a b, and it is attained at the point y naught in a b. Note that this x naught and y naught need not be unique. So, note that there can be more than one point at which the minimum or maximum value is attained. For example, we can have a function so if you see this function, it attains this maximum value at these 2 points. So, these two are points of maxima for this function. In fact, if we take f of x to be the constant function, then the minimum as well as maximum value is that constant and it is attained at every point on the interval. But there is only one, but there is a unique minimum value and a unique maximum value. Now, the question is how to find the minimum and maximum values. So, let me give some examples. Example 1, suppose we have this function on an interval a b. Here if you see, the maximum value of this function is this number capital M and the minimum value is this number small m, and these are points. So, this is my x naught and y naught. So, in this example, the minimum value and the maximum value can be attained at points in the open interval a b. Another case would be that these values, suppose I have a function like this. So, I take this function from -1 to 1 f x equal to mod x on the interval -1 1. In this case, the minimum value is attained at x equal to 0, which lies in the open interval -1 to 1, whereas the maximum value is attained at x equal to plus minus 1, which are the end points of the closed interval -1 1. So, it is possible that the minimum value or maximum value can be attained at the end point. Also, in this example, at the point of minima, at the point of minima, that is at x equal to 0, the derivative f prime 0 does not exist. Whereas, if you look at the previous example, in this example, the point at which the minimum and maximum are attained, we see that f prime x naught is 0 and f prime y naught is also 0. So, what we have seen from these examples, that the minimum value or maximum value can be attained either in the open interval a b, or it might be attained at one of the end points. So, conclusion, the points of minima and maxima these, let me call this as the points of absolute minima, because this gives me the greatest value and the least value. So, the point of absolute minima and maxima of f of x on a closed interval a b can be either one of the end points or an interior point. Another theorem that we have seen before, recall theorem, if f of x has minima or maxima on the open interval a b, then either the derivative does not exist at that point. For example, in the example f x equal to mod x, we have this, or the derivative f prime x is equal to 0 at that point. So, such a point we will call critical points. So, we write definition for a continuous function f of x on an interval a b, the critical points of f are the points where the function, where f is not differentiable or where the derivative equals 0. So, now in order to find the points of minimum and maximum, what we have to look for. So, to find the points of maxima and minima, and the maximum and minimum values, maximum value and minimum value, what we do is the following. Step 1, find all critical points in the open interval a b, that is the points where f prime x is equal to 0 or f prime x does not exist. So, we check for the points where the derivative does not exist and then find the points where f prime x is equal to 0. This gives me all the critical points. Step 2, find the values of f of x at all critical points. Step 3, find the values of f of x at the end points. That is, find what is f of a and f of b. And then we know that the minimum and maximum values are attained at one of these. So, find the minimum and the maximum values among those obtained in steps 2 and 3. And this gives us the minimum and maximum value. This gives us the minimum and maximum values and also the points of global minima and maxima. That is the point where this minimum value and maximum value are obtained. This global, or this is also called absolute minima and maxima. This is to differentiate from the concept of local minima and local maxima that we discussed before. So, let us look at an example. So, find the maximum and minimum values of f x equal to x cube minus 6 x square plus 9 x plus 15 on the interval, let us say minus 1 to 2. So, what we do is, first we find the critical points, find the critical points. So, here since f x is a polynomial, f prime x exists at all points. So, there is no point where f prime x does not exist. Now, if I find f prime x, this is equal to 3 x square minus 12 x plus 9. Then to find the critical points, we have to find the zeros of f prime x. Find the zeros of f prime x. So, we equate 3 x square minus 12 x plus 9 equal to 0, that is x square minus 4 x plus 3 equal to 0, and this gives us x minus 1 times x minus 3 equal to 0. So, x is equal to 1 or x equal to 3. Now, x equal to 1 lies in the interval -1 2, whereas x equal to 3 lies outside the interval. So, in this case, so x equal to 1 is the only critical point in the open interval -1 to 2. Then we find the values, of f of x at the critical points as well as the end points. So, at the critical point f of 1 is equal to f of x was x cube minus 6 x square plus 9 x plus 15. If we put x equal to 1 here, we get 1 minus 6 plus 9 plus 15. This gives us 19. And then at the end points, f at -1 is equal to -1 cube minus 6 times -1 squared plus 9 times -1 plus 15. This is equal to -1 minus 6 minus 9 plus 15. So, this gives -1, and at the other end point f at 2 is equal to 2 cube minus 6 times 2 squared plus 9 times 2 plus 15, and this is equal to 8 minus 24 plus 18 plus 15, and this gives equal to 17. Now, among these, so we have these three values 19, f at -1 is -1 and 17. We look at the minimum and maximum among these. So, the minimum value is -1, which is attained at one of the endpoint -1, and the maximum value is 19, which is attained at the critical point x equal to 1. Right. So, this example shows how to find the minimum value and maximum value of a continuous function on a closed interval. Now, consider another example. Suppose I define f of x equal to x plus 1 by x for x belonging to r minus 0. So, this function f of x is x plus 1 by x. This is not defined at 0, but it is defined everywhere else. Now, the question is find the minimum and maximum value of f of x if they exist. So, first thing note that since this function f x equal to x plus 1 by x is defined for all real numbers except 0, we are not considering this function over a closed interval. So, we do not know whether the minimum and maximum values are defined or not, these minimum and maximum values exist or not. So, if they exist, we need to find that. So, let me write this as remark. Since here we are not considering f of x over a closed interval, the minimum value or the maximum value need not exist. So, how to find this? So, first of all note that this f of x equal to x plus 1 by x, this can be written as x square plus 1 over x. This is defined for all x not equal to 0. Now, note that if I take x square plus 1 minus 2 x, this is nothing but x minus 1 whole squared, which has to be greater than or equal to 0. So, what does this say? This implies that x square plus 1 must be bigger than equal to 2 x, and therefore, this implies x square plus 1 by x, this is greater than equal to 2 if x is positive, then I can divide by x and this will be greater than equal to 2, and if x is negative, then this will become one by x. Of course, in this case x square plus 1 is always positive and x is negative. So, this will be less than 0 if x is negative. So, if we consider, so on the interval, if I take the interval instead of taking all non-zero real numbers, if I take the positive real numbers 0 to infinity, f of x equal to x square plus 1 by x, this is greater than equal to 2. So, this says that also at x equal to 1, if you see this, if I put x equal to 1, then this is equal to 0, and therefore, at x equal to 1, f of x takes the value 2. Hence, f of x has minimum value two attained at x equal to 1 on the interval 0 infinity. Now, what about the maximum value? Is there any maximum value on the interval 0 infinity? So, if you see this function f x equal to x plus 1 by x, note that this function, this goes to positive infinity as x goes to 0 plus, and also this goes to positive infinity as x goes to positive infinity. So, therefore, f x has no maximum value on the interval 0 infinity. Now, for the now on the interval, if you look at minus infinity to 0, we have f x equal to again x plus 1 by x. So, if you see, we are replacing x by negative x, this is x and 1 by x, these are negative. So, this is same thing as negative of minus x plus 1 by minus x, and now we know that here minus x is positive, minus x is positive. So, by using the previous one we can tell the, so therefore, on minus infinity to 0 we have minus f of x, this is equal to minus x plus 1 by minus x. Now, here because minus x is positive, we have already seen that this is greater than equal to 2 by previous part. So, therefore, f of x must be less than equal to minus 2 on minus infinity to 0. Also, as x goes to negative infinity, f x equal to x plus 1 by x, this goes to negative infinity also, and as x goes to 0 from the left, again f of x goes to negative infinity. So, f x has minimum value minus 2 obtained at x equal to minus 1, if you evaluate you get minus 2, and it has, sorry, this is the f x has maximum value minus 2, which is obtained at x equal to minus 1, and it has no minimum value on the interval minus infinity to 0. Another way is just like we did for the first part. So, for x less than 0, what we do is, if I write x square plus 1 plus 2 x, this is equal to x plus 1 whole squared. So, this is again greater than equal to 0, which implies x square plus 1 is greater than equal to minus 2 x, and then this implies x square plus 1 by, if I write minus x here, this will be greater than equal to 2. This is because here minus x is positive. So, if I divide by minus x, the inequality is same, and this implies that x square plus 1 by x, this is less than equal to minus 2, which is same as what we have obtained here. Now, can we use calculus to derive the same conclusion? So, let us look at if we can do this. So, we have f of x is given to be x plus 1 by x for x not equal to 0. Now, we know that this function f of x is continuous and differentiable for all non-zero x. Let us calculate the derivative. If we find f prime x, derivative of x is 1, derivative of 1 by x is minus 1 by x square. So, derivative is 1 minus 1 by x square. Now, what we will do is we will see the sign of f prime x. So, if we see this f prime x, this is equal to 0 if and only if x square is equal to 1, that means x is equal to plus or minus 1. So, the derivative is 0 at minus 1 and 1. Also, if we look at now the interval, so we have minus 1, 1. So, if we look at this, if x square is greater than 1, this implies 1 by x square will be less than 1. So, f prime x is 1 minus 1 by x square, this will be greater than 0. And if x square is less than 1, then 1 by x square is greater than 1, which implies 1 minus 1 by x square is less than 0. Now, x square is less than 1 means x is between minus 1 and 1. So, in this interval the derivative is negative. So, f prime is negative here, and x square greater than 1, x square less than 1 is equivalent to x is between minus 1 and 1, and x square greater than 1, this is equivalent to x is greater than 1 or x is less than minus 1. So, the derivative is positive in the interval 1 to infinity, and derivative is positive also in the interval minus infinity to minus 1. So, f prime x is positive on minus infinity to minus 1 and also on 1 to infinity, and f prime x is negative on, I cannot write minus 1 to 1 because at 0 the function is not defined. So, on minus 1 to 0 f prime x is negative, and also on 0 to 1 f prime x is negative. Now, recall that f prime x positive implies f is increasing. In fact, strictly increasing in that interval, and f prime x negative, this implies f is decreasing. So, what we know is that the function, thus f of x is increasing on minus infinity to minus 1, and then f prime x from minus 1 to 0 is decreasing on minus 1 to 0, then again it is decreasing on 0 to 1 and increasing on the interval 1 to infinity. So, if we see this, what we have is we have minus 1 and 1 where the derivative is 0. The function is increasing from minus infinity to minus 1. Let us look at first for the positive part what happens. So, on 0 to 1 the function is decreasing and increasing from 1 to infinity. So, this implies, let us draw this again, minus 1, 0, 1. What we have is the function is increasing in this interval, decreasing in this interval, then again it is decreasing on this interval and increasing on this. This means that this point at minus 1 we have, this is a point of local maximum and 1 is point of local minima. So, this first derivative test, it tells you what happens to the function. Also what we know is that as x goes to 0 from the right, the function goes to positive infinity. So, we have at 1 the value of the function is 2, and then the function is decreasing up to 1 and then it is increasing from in 1 to infinity. So, the graph of the function will look like this, and at x equal to 1 the derivative is 0, and similarly on the negative side at x equal to minus 1 the value of the function is minus 2, and then the function is, it goes to negative infinity as x goes to 0 from the left side, and it also goes to negative infinity here, and we have a local maximum at this point minus 1, right. So, this is the how the graph of the function will look like. So, from this we can conclude that on 0 infinity f x has no maximum value, but has the minimum value two at x equal to 1 and on minus infinity to 0 f x has no minimum value, but has a maximum value minus 2 at x equal to minus 1. Note that if we consider over the whole interval, on r minus 0, this function f of x equal to x plus 1 by x has no minimum value and no maximum value. Because the function tends to minus infinity as x goes to negative infinity, and it tends to plus infinity as x goes to plus infinity. So, it cannot have minimum or maximum value on the whole interval r minus 0 on the whole less, but if we take only on the positive real number, then it has minimum value at 2 at x equal to 1, and on the negative real number it has maximum value minus 2 at x equal to minus 1. Okay, so this finishes today's lecture. In the next lecture, we will learn about the second derivative test to find the local minimum and local maximum, and also some other applications of derivative. Thank you.